Hello and welcome. I am Dr. Pauline Fu. In this video, I will present hypothesis test for independence and for homogeneity of proportions. Learning objectives include perform the test for independence, perform the test for homogeneities of proportions, chi-square test for independence used to determine whether there is an association between a raw variable and a column variable in a contingency table. The null hypothesis is that the variables are not associated. Variables are not associated. Not associated is the same as independent. The alternative hypothesis is that variables are associated or dependent. Maybe I'll try to use the same color. The alternative said variables are associated or dependent. So when we write down the H0 null hypothesis, we say the variables are independent. And the alternative hypothesis H1, the variables are not independent. Let's take an example because we are going to use the chi-square test, and chi-square test need expected values. So we are going to determine the expected counts first. In a poll, 883 males and 883 females were asked, if you could have only one of the following, which would you pick? Money, health, or love? Their responses are presented in the table below. Determine the expected counts with each cell, assuming that gender and responses are independent. Okay, so we ask students question. If you have choice, just select one among money, health, love. 82 men select money. 46 women select money. 446 men select health. 574 women select health. 355 men select love. And 273 women select life. How many total males? If you add all these together, you have 883 total males. And the total female, 893. Okay. I actually did a similar survey in my class. I asked the same question. If you have just one choice among money, health, love, which one would you choose? And I counted the frequency. It is actually the result similar to this one, although I do not have large sample, but it is proportional, okay, to these results. So first, we are going to count the raw total. How many total for men? Okay, so you add these three numbers, you get total number for men. And how many total for women? You add these three numbers, you get total women. And then we calculate column totals. So for column totals, you add these two numbers, 82 plus 46, equal to 128, 446 plus 574, 1020, 355 plus 273, 228. Okay, and if you add all these three numbers together, you get 1776. Or if you add total male, man, and total woman, you'll come up with 1776. Okay, so we calculated the row total and the column totals. Next, we compute the relative marginal frequency for row variable and the column variable. Okay, what we use the row total 883 divided by grand total 1776, and we get relative frequency. It is 0.4972. Similarly, use the row total for woman divided by grand total. You get 0.5028. And now for this column here, relative frequency. So total people who select money, 128, divide grand total, 1776, you get this frequency. Okay, and similarly, you can figure out the relative frequency for people choosing health, choosing love. Okay. And once we get those relative marginal frequency, and we can use the multiplication rule for probability. Okay, so we assume gender response are independent. We then use multiplication rule for independent events. Remember the rule said, if A and B are independent, probability of A and B equal to probability of A times probability of B. Provide A and B independent. Okay, independent. So we can calculate the proportion of observations we would expect in each cell. Okay, so how? If you use this number, 0.4972, multiply 0.0721, you would get this number here. So this number is the result of 0.4972. Try to write 0.4972 times 0.0721, 0.0721, and you get this number. Similarly, you can get 0.2855 using 0.4972 times 0.5743. Okay, so you get this number. Okay, and once we get all the numbers, we then, this is the expected frequency, and we use the total number, 1776 times the expected frequency, and we'll get 63.58. Okay. So this is how we calculate expected counts. So this is one way to do it. Another way to do expected counts, you use row total times column total divide grand total. So if I were to calculate the expected count for man who chose money, if I were to calculate the expected count, I use row total, so expected count. I use row total for this number, that is 883 times column total 128 divide grand total 1776, and this will give me the expected number here 63.5808. Okay. In the past, from the past experience, most students will choose this method: raw total times column total divided by grand total to get expected value. Okay. So this formula, most students will choose this one. And once you have expected value, you then use observed minus expected, square it, then divide expected, add them all, you get chi-square. And this chi-square follows chi-square distribution, means looks like this way, chi-square distribution. Okay, with the degree of freedom is number of rows are -1 times number of column -1. So for example, this question, okay, original question, how many row, number of row, we have 2, man, woman. How many column, number of column, we have 3, money, health, love. Okay, so the degree of freedom equal to number of row -1 times number of column -1. It comes up with 2 minus 1 times 3 minus 1. So the degree of freedom for our example is 2. Okay. And also make sure we have the requirement for chi-square test. The first requirement, all expected frequencies are greater than 1. 2, no more than 20% of the expected frequencies are less than 5. Okay, so that is the chi-square distribution. Now let's use chi-square test for independence to see if the column variable is independent with the row variable. Okay, so step 1, determine the null and the hypothesis test. Alternative test, null hypothesis H0, the row variable and column variable are independent. H1 said the row variable and the column variable are dependent. You see H0 and H1 are opposite to each other. One of them is correct. Step 2, we choose level of significance alpha. Okay, oops. Step 2, level of significance alpha. Step 3, there are some sub-steps in step 3. We need to calculate the expected frequency or expected value. Remember what is expected value? Row total times column total divided by grand total. That is the expected value. Row total times column total divide grand total. Okay. And verify the requirements for chi-square test are satisfied. One requirement said all expected frequencies are greater or equal to 1. Second requirement, no more than 20% of the expected frequencies are less than 5. So now we can calculate test statistic. Use observed minus expected, square it, divide expected, and add them all. That is chi-square. So chi-square is the first observed minus expected squared over E. Okay, this is the first one. Then do the second one. The second observed minus the second expected squared divide expected. Keep on going. Okay, that is sigma. Add them all. And step 4, determine critical value, chi-square with r minus 1 times c minus 1 degree of freedom. You can find critical value from the table, or you can find critical value from Excel. Oops. Once you have critical value, suppose it is subscript alpha, chi-square subscript alpha. Critical value decide rejection region. Rejection region, also called critical region. And this area is alpha. The area corresponding to this point is a critical value. Okay. And then remember in step 3, you get test statistic. If test statistic is here, you reject H0. Means row variable and column variable are dependent. If your test statistic is here, you do not reject H0. Means row variable and column variables are independent. Okay, that is critical approach. And for p-value approach, once you get this test statistic, you found the p-value. This is test statistic. Remember what is p-value? P-value is the area corresponding to test statistic. So this area is p-value. And then you compare p-value with alpha. If p-value is smaller than alpha, you reject H0. And when p-value is greater than alpha, do not reject H0. So that is the p-value approach. So now let's do the hypothesis test for the examples we have seen before. So this table, among money, health, love, which one would you choose? This is the survey results. And the question is, test the claim that gender and the response are independent at 0.05 level of significance. Okay, independence means the answer you choose has nothing to do with whether you are man or woman. Okay, so we are going to test if this claim is true or not true. Step 1, state null hypothesis. H0 and alternative hypothesis H1. H0 said gender and response are independent. H1 said gender and response are dependent. Step 2, choose alpha 0.05. Step 3, calculate the expected frequency. Okay, the number in the bracket are expected frequency. Remember, how do we calculate this expected frequency? We use row total times column total divide grand total, and that is my expected frequency. Okay, and those numbers are observed value. So observed value, use a big letter O, and expected value in the bracket. You have observed value, you have expected value. Bracket is the expected value. And once you have O, you have E, calculate test statistic. Okay, it is O minus E, observed minus expect, square, divide E, and add them all. Add another one, add another one. Okay, so how many we need to add? We need to add 6 items total. 1, 2, 3, 4, 5, 6. We need to add 6 items together. Okay, each item we are going to use O minus E square divide E. So for example, the first one, O is 82. So we are going to use 82. E is 63.58. 08. So O minus E square divide E, 63.5808. So this is, you just finished the first one. You need to repeat yourself 6 times. Okay, so do the next one. O is 446. E, 507. Square it. Divide E, 507.048. Okay, so you keep on going. And the result you get is 36.82. That is your test statistic. Okay. Once you have test statistic, we can use the classical approach to find the critical value. Okay, use 2 degrees of freedom, y, number of row minus 1 times number of column minus 1. And alpha is 0.05. Okay, so let's go to the table to find the critical value. Then we use Excel. Okay, so when you use table, alpha 0.05, degree of freedom is 2. So this is the chi-square distribution. Okay. Locate degree of freedom 2. Then locate alpha, the intersection part of 2 with this alpha is this number, 5.991. So this is a table method. Another method, you can use Excel. And for Excel, you just type in equal CHISQ chi-square dot INV means critical value dot RT chi-square in chapter 11 is a right tail test. Okay. So probability 0.05, degree of freedom is 2. Press enter, you get 5.991. And this is the formula here. Okay. So we found the critical value for chi-square. Oops. Once you found the critical value for chi-square, so what? You draw the diagram of chi-square distribution, and you label this test statistic. No, critical value. You label critical value. Why? Because critical value decides rejection region. So this is rejection region. Rejection region. And then you locate test statistic 36.82 test statistic. So 36.82. is here. Obviously, test statistic is in the rejection region, so you reject H0. Okay, so your final conclusion is row variable and column variable are dependent, means gender and response are associated with each other. So this is your classical approach conclusion. Next, let's do the p-value approach. Okay, remember for p-value approach, you need to find the p-value. And what is p-value? P-value is the area corresponding to test statistic. And remember in test step 3, we calculated test statistic is 36.82. So test statistic decide p-value. P-value is here. This is p-value. Okay. So how do I find this area? Once you have this point, you go Excel. Okay. I actually strongly suggest use Excel because sometimes table is not accessible. So equal chi-square, because we want to find p-value. So dot dist distribution and dot rt. X is 36.82. Degree of freedom is 2. So that's how you found the p-value using Excel. Wow, this is a very small number. This E negative, negative 8 means 10 raised to power negative 8. It is almost 0, this number. Okay, so this is the formula to get p-value. Okay. I already copied the formula here, and this is the result. This number is the same as 1.01074. This is scientific notation, means times 10 raised to power negative 8. This number almost equal to 0. So p-value almost 0. When p-value is almost 0, obviously, this p-value is 0. Okay, so p-value obviously is smaller than alpha. This is p-value. And when p-value is smaller than alpha, you reject H0. Same conclusion as we got from classical approach. Reject H0. Okay. So far, we did hypothesis test for independence. Next, we'll do hypothesis test for homogeneities of proportions. The test for homogeneity of proportions is that we want to test whether different proportions have the same, whether different populations have the same proportion of individuals with some characteristics. In short word, whether we have same proportion for different populations. Okay. The procedure for the test of homogeneity exactly the same as what we did before for test for independence. Exactly the same procedure. Okay. So let's do this example. Okay. The following questions were asked of a random sample of individuals in 1992, 2002, 2008. Would you tell me if you feel being a teacher is an occupation of very great prestigious? The results of survey are presented below. Okay. Wow. So you see in 1992, many choose no. So the question is, teacher is an occupation of a very great prestigious. Okay, many people select no. And in 2008, you got to see the difference. So in 1992, 418 select yes, 702 select no, but this difference actually decreased in year 2008. Okay, so anyway, we want to test the claim that the proportion of individuals that feel being a teacher is an occupation of very great prestige is the same for each year at 0.01 level of significance. Actually, by just looking at the number, we have feeling the answer is not the same for each year as I analyze here. Okay, you compare this number, the difference. You just directly looking at the data, you have intuitive, okay? It is not the same each year, but we need scientific proof. We need to conduct hypothesis tests to reach this conclusion, to support our intuition. Okay. So step one. By the way, we are comparing three proportions. One proportion is for year 2019, one proportion for year 2002, one proportion for year 2008. Okay, so we say null hypothesis. Those three proportions are the same. Alternative said at least one of the proportion is different from others. Okay. And then we, step two, specify alpha. This time we use 0.01. Okay. And step three, we calculate the expected number as shown in the bracket. And how do you calculate the expected number? You have to do the raw total. You have to do the raw total here. There is a raw total number, and you have to do the column total here, column total here, column total here, and you have to do the grand total here. And then expected number, how do you calculate the expected number for yes in year 1992? You use raw total, this number, times this number, divide grand total, you get expected number. And the result is 475.554. Okay, similarly, you get other expected number. Okay. And then you got, those are observed number, observed, big O. And then you get expected, use the red color, use the E, expected. Okay. And then you need to calculate test statistic. But before you do calculation, check the requirements. Okay. None of the expected values are less than 5. Okay. So requirements are satisfied. Okay. And then test statistic is use observed minus expected squared divide expected. You do this for six cells, okay, and you come up with chi-square test result 24.74. Okay, so this is test statistic. So guess what we are going to do next? Critical value. Okay, so we are going to use a classical approach. Okay, we need to find the critical value. Okay, critical value, you need 2 items, 1 degree of freedom, 2 alpha. Okay, so degree of freedom, number of row minus 1, number of column minus 1 times together equal to 2. And then locate alpha 0.01. Okay, so let's go to the table to find this critical value. So going to erase. Locate degree of freedom is 2. And then alpha 0.01 here. So the intersection between row 2 and this alpha is 9.210. This is the critical value. Okay. So this is used the table. You can use Excel to get this critical value. Okay. So the critical value is, I'm going to write down here, equal K CHISQ dot INV dot RT. Okay. Probability 0.01, degree of freedom 2. See, you get the same number. I'll just copy this here. So this using Excel, you get the same number as we get from the table. Okay, critical value. So now you have critical value. So what? You draw a diagram of chi-square distribution, and then you label the critical value 9.21. Why you need to label the critical value? Because critical value decide rejection region. This is rejection region. Okay. And now locate test statistic in this picture. Test statistic 24.74. Okay. So 24.74 is here. This is test statistic, test stats statistic. And this red one is a critical value. Critical value. Obviously, test statistic is in the rejection region, so you reject H0. Okay. Therefore, you remember what is your H0? You reject this H0 and in favor of H1. So your final conclusion, at least one of the proportion is different from others. Okay, so that is the final conclusion based on classical approach. Remember, each time after we finish classical approach, we'll do p-value approach. Okay, so this is, we are going to turn to p-value approach. So remember, what is the p-value? P-value is the area corresponding to test statistic. So label the test statistic 24.74. And this area is p-value. This area corresponding to test statistic is p-value. And how do we find this area? Once we have this point, go Excel. Okay. So I'll do it here. So equal CHISQ dot DIST dot RT. X is 24.74. Degree of freedom is 2. Okay. And we have this number here. I will copy this one. Just try to move this text box here. Okay, so that is the p-value. So the result of the p-value you see is 4.244 E negative. I will also copy this one, Control C, and then Control V. So try to move this box here. this overlapped. They all go together. Right. Okay. Delete this one. So I need to see the formula. Maybe I recopy the formula here. This is the formula. Control C. Here. Okay, so this is the formula, and this is the result. This p-value is a very small number. It is 4.244 times 10 raised to power -6. This number almost 0, roughly equal to 0. And this p-value obviously smaller than alpha. Okay, p-value almost 0, smaller than alpha. So we reject H0. Okay, in favor of H1, reject H0. So our final conclusion, at least one proportion is different from others. Okay. All right. So in summary, I did 2 tests. One test is a hypothesis test for independence. The other test is for homogeneity of proportions. Both tests are use chi-square test, and both tests are use classical approach and p-value approach. For critical values, I demonstrated using the table and Excel. Okay. Hope you enjoyed this video. Thank you so much for your time. I'll see you next time.